Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to picture something for a second. Close your eyes if you can, and just imagine the ocean at night.
Okay.
But we are not talking about a calm, peaceful ocean reflecting the moonlight. Picture a vast, absolutely pitch black expanse.
Right.
It's terrifyingly deep and completely chillingly silent. You were suspended in this water, and moving through this dark expanse without a single sound are massive ancient rocks.
Just drifting.
Exactly. Some are the size of cars, some are the size of city blocks, and, a few are the size of entire mountain ranges.
Yeah, which is a terrifying thought.
Right. They are just hurtling through the darkness, completely unbothered by anything around them, just driven by momentum that was set in motion billions of years ago during the violent birth of our solar system.
Yeah, just ancient kinetic energy.
Now, here's the truly unsettling part of this thought experiment. You are sitting in a tiny, incredibly fragile glass boat right in the middle of this ocean.
Oh, wow. Okay.
You have a flashlight, but, the beam is weak. It only penetrates a few feet into the murk. Most of the time, the massive rocks pass safely in the distance.
You don't even know they are there.
You have no idea. But occasionally, one of those colossal silent shapes crosses right through your path. It slips out of the dark, skims just past the fragile hull of your glass boat, and disappears back into the void before you even have a chance to draw a breath, let alone, brace for an impact.
That's a profoundly visceral way to describe the reality of our orbital neighborhood. It really strips away the abstract math.
It puts you right there, right?
It does. It puts the listener right into the physical vulnerability of our situation. Because we tend to think of space as empty, but we are floating in a dynamic, incredibly active shooting gallery.
A shooting gallery, yeah.
Our planet sits in a chaotic web of orbital trajectories. And for a very long time, humanity's strategy regarding near-Earth objects has basically been to point our flashlights into the dark, cross our fingers, and hope the beam catches the big ones.
While they're still far enough away to do something about them.
Exactly.
And that terrifying reality is the core mission of our discussion today. We are looking critically at our current and frankly alarming limitations in understanding what these asteroids actually are.
Because just knowing a rock is out there in the darkness isn't enough.
Not even close. We have to know what it is made of, how it is held together, and where its momentum is taking it.
Right.
So we are going to explore a brilliantly unorthodox space mission architecture. It's proposed by researchers in the UK, and it's called REMORA. REMORA. Yep, standing for Rendezvous Mission for Orbital Reconstruction of Asteroids. And it is designed to completely rewrite the rule book on how we interact with these ancient celestial bodies.
And we really need to set the stakes right at the top here, because analyzing REMORA isn't just an academic exercise in geology.
No, not at all.
We aren't figuring out ways to catalog different types of space rocks just to, fill out a textbook on the early solar system. This architecture is fundamentally driven by the urgent need for planetary defense.
It's about survival.
It is. We are approaching a very real, very tangible deadline. In the year 2029, humanity is going to experience an incredibly close encounter with a massive asteroid named Apophis.
Apophis, yeah, we are definitely going to get into that.
And beyond Apophis, we have this glaring, terrifying vulnerability in our observational network known as the sunward blind spot.
The blind spot.
Right. There are entire vast regions of the sky where our most powerful ground-based and orbital telescopes are rendered completely blind by the overwhelming glare of our own sun.
Like staring into a spotlight.
Exactly like that.
Yeah.
Earth is entirely unprotected from any trajectory approaching from that specific vector. If a kinetic threat comes at us out of the sun, we will not see it until it is literally entering our upper atmosphere.
Okay, let's unpack this, because before we can fully grasp the elegance of how the REMORA architecture fixes the problem, we have to establish the baseline.
The baseline of how we currently try to study these things.
Yeah, how we currently try, and often fail, to study these near-Earth objects. Right now, our primary tools are remote sensing.
Right. Optical telescopes, radar.
Yeah, we use ground-based optical telescopes. We use planetary radar, like the Goldstone Solar System radar out in California. We use infrared orbital observatories.
All looking from a distance?
Exactly. And all of these tools suffer from a fundamental limitation. I call it the skyscraper facade dilemma.
The skyscraper facade dilemma. Okay, explain that.
Well, imagine you are an engineer tasked with determining if a massive skyscraper is going to collapse in an earthquake.
Okay.
But you are not allowed to go inside. You have to stand across the street.
Just looking at the outside.
Right. You can look at the tint of the exterior glass. You can bounce a laser off the steel window frames. You can take thermal images to see which side of the building is getting hit by the sun.
But you're stuck on the street.
You're stuck on the outside. To truly know the structural integrity of that building, to know if the internal load-bearing columns are solid, reinforced concrete, or if they are structurally compromised and hollowing out, you have to walk through the front door.
You have to get inside.
Yeah, you cannot determine the internal macro porosity of a structure just by analyzing how photons scatter off its outermost layer.
That captures the physics of the problem perfectly. When we use spectroscopy through an optical telescope, we are really just analyzing the reflectance spectra of the asteroid.
The surface light.
Exactly. We measure which specific wavelengths of sunlight are absorbed and which are reflected by the minerals on the surface.
So that tells us what the dust on the outside is made of.
Basically. It tells us if the outer crust is rich in silicates, or carbonaceous material, or metallic iron.
Okay.
And when we use synthetic aperture radar, we are bouncing microwave pulses off the object. That gives us a radar cross-section, which can reveal the asteroid's general shape, its rotation period, and surface roughness.
So we get the ship and the spin.
Right. But both optical light and radar waves are superficial in this context. They scatter off the boundary layer. They cannot penetrate hundreds of meters of rock to reveal the interior mass distribution.
They just bounce off.
Yeah. And from a planetary defense perspective, that blind spot is a catastrophic lack of actionable intelligence.
Because if we spot one of these things on a collision course and we have to physically move it, the internal structure dictates everything about how we apply force, right?
It dictates the entire physics profile of a deflection mission. Take the concept of a kinetic impactor.
Okay.
This is the strategy where we launch a heavy spacecraft and intentionally ram it into the asteroid at extremely high velocities.
Just playing cosmic billiards.
Basically, yeah. To alter its orbital momentum. We recently proved this concept works with NASA's DART mission.
The double asteroid redirection test.
Right, which successfully altered the orbit of the asteroid Dimorphos. But the success of a kinetic impactor is heavily dependent on something called the beta factor, or the momentum enhancement factor.
Which is essentially how much extra push you get from all the debris spraying back out into space after the crash, right?
Correct. If you smash an impactor into a monolithic, incredibly dense, solid iron asteroid, the energy transfer is relatively straightforward.
Like hitting a bowling ball.
Yeah, but the debris blown backwards might be minimal. However, many asteroids are what we call rubble piles.
Rubble piles. So they aren't solid.
No, they aren't single solid rocks. They are loose amalgamations of boulders, gravel, and dust.
Just held together by gravity.
Their own incredibly weak collective microgravity.
Wow.
So if you slam an impactor into a highly porous rubble pile, the impactor might just burrow deeply into the loose material.
Like shooting a bullet into a sandbag.
Exactly. It compresses the empty void space inside the asteroid.
Oh.
The rubble pile absorbs the kinetic energy like a giant celestial sponge.
Oh, man. So it doesn't move.
The beta factor changes completely. The asteroid might barely alter its trajectory at all, or worse.
What's worse?
If you hit it with too much energy, you might exceed its weak escape velocity and shatter it into a shotgun blast of fragments.
Oh, God. So instead of one rock hitting Earth, it's 100.
A shotgun blast of highly destructive fragments that stay on the same collision course with Earth. You absolutely cannot design an optimal deflection mechanism without a high-fidelity model of the internal structural integrity.
And you just cannot get a high-fidelity internal model from a telescope on a mountain in Hawaii.
No.
You have to get up close and personal with the rock. Which brings us to a really interesting geopolitical and economic paradox currently playing out in the United Kingdom regarding space science.
Right, the UK paradox.
Because the UK possesses a staggering amount of intellectual capital in planetary science and astrodynamics.
Huge amount.
Yeah, researchers from institutions like Imperial College London or the University of Liverpool, where the core REMORA concept is being spearheaded, they are globally recognized heavyweights.
Absolutely.
They don't just sit on the sidelines. They are deeply integrated into the most complex, headline-grabbing international missions of our era.
Like the DART mission.
Right. UK teams were essential in analyzing the impact data from the DART mission we just talked about. They played vital roles in the OSIRIS-REx mission, which executed an incredibly complex touch-and-go maneuver.
To snatch a physical sample of the asteroid Bennu.
Right, and bring it back to Earth. The UK's scientific footprint is everywhere.
They are consistently producing the algorithms, the data processing techniques, and the scientific analysis that make these billion-dollar flagship missions successful.
But, I look at that reality and I have to ask the obvious administrative question.
Sure.
If I am sitting on a parliamentary budgetary committee looking at the national checkbook, I'm thinking, our scientists are already getting access to the best data in the solar system by collaborating with NASA and the European Space Agency.
Why do we need our own stuff?
Exactly. Why do we need to aggressively fund our own UK-specific domestic mission architecture? It seems infinitely cheaper to just keep paying a small membership fee to the ESA.
Let the Americans and Europeans build the big rockets.
Right. Let them build the billion-dollar rockets and probes, and let our scientists analyze the data when it gets beamed back. Why try to build a sovereign deep space pipeline?
What's fascinating here is the stark difference between holding a seat in the passenger cabin versus holding the steering wheel.
Oh, that's a good way to put it.
When a nation operates solely as a contributor to international flagship missions, no matter how valued their scientific input is, they are ultimately subjected to the strategic priorities of the lead agency.
The agency paying the bills.
Right. If you are riding shotgun on a NASA mission, NASA's decadal survey dictates the target asteroid. NASA engineers design the primary bus architecture. NASA sets the launch window.
So the UK is just along for the ride.
The UK scientists might be granted a principal investigator role on one specific onboard spectrometer, or they might get priority access to the telemetry data, but they do not control the mission parameters.
But so they are brilliant analysts, but they are entirely reactive. They have to wait for someone else to decide it is time to go look at a rock.
And when you are dealing with planetary defense, or looking toward the massive economic potential of future asteroid mining, reactive posture is a strategic vulnerability.
You can't just wait around.
You do not want to be entirely dependent on the fluctuating budgets of the U.S. Congress or the complex multinational negotiations of the ESA to determine if or when a specific near-Earth object gets investigated.
Because what if they say no?
Exactly. Developing a domestic pipeline allows a space sector to rapidly prototype its own sovereign engineering concepts, validate its own hardware in the void, and respond to threats or economic opportunities on its own timeline. It builds an industrial base at home.
But the reality is, sovereign capability is breathtakingly expensive.
Very.
If the UK wants to pick its own targets and steer its own ships, it cannot do it by mimicking NASA's playbook. A country dealing with standard domestic economic pressures cannot just casually authorize a $1 billion flagship mission to go map an asteroid.
It's just not going to happen.
No. To solve this paradox, to achieve independent exploration without bankrupting the science directorate, you have to get ruthlessly, almost uncomfortably creative.
You really do.
You have to abandon the idea of the massive gold-plated spacecraft. And that severe budgetary constraint is exactly the evolutionary pressure that birthed the REMORA architecture.
We have to define budgetary constraint in this context, because the numbers associated with the REMORA proposal are almost hard to believe for anyone familiar with aerospace procurement.
They're shockingly low.
Right. The white papers classify this as a mini F-class mission, and they are targeting a total mission cost in the neighborhood of 50 million euros.
We really need to pause on that number because 50 million euros sounds like an astronomical sum in everyday life.
Oh, sure.
You could fund a mid-sized hospital for years, you could build infrastructure, but in the realm of deep space exploration,
It's nothing.
50 million euros is essentially a rounding error. It is the aerospace equivalent of trying to build a Formula One car using the spare change you found under the sofa cushions.
It demands a total paradigm shift in engineering. For comparison, the OSIRIS-REx mission you mentioned earlier had a life cycle cost pushing well toward $1 billion.
Wow.
The DART impactor, which was relatively straightforward because its entire job was to crash and die,
Right. Just hit a rock.
it still cost over $300 million. Even the most stripped-down, aggressive Discovery-class interplanetary missions at NASA rarely drop below the $200 million threshold.
So 50 million is just, it's insane.
To propose intercepting a fast-moving, chaotic body in deep space, characterizing its mass distribution, and operating a scientific payload for 50 million euros means you cannot use standard deep space hardware.
You have to rethink everything.
You cannot afford the massive, radiation-hardened command processors. You cannot afford the huge, high-gain parabolic antennas. Every single subsystem has to be miniaturized, stripped of excess mass, and fundamentally reimagined.
Which leads the researchers to abandon the concept of the monolithic probe entirely. REMORA doesn't send one big, expensive box into space.
No, it doesn't.
It relies on a swarm. The proposal calls for a fleet of 6 autonomous CubeSats. And the biological inspiration for this approach is baked right into the acronym. They are looking at the remora fish.
Right, the little fish that stick to sharks.
Exactly. If you watch footage of a great white shark or a massive manta ray gliding through the ocean, you almost always see these tiny, slender fish suctioned onto their sides or swimming in absolute synchronicity just inches away.
Right.
The remora fish don't waste their own energy swimming across the entire ocean. They let the apex predator do the heavy lifting, hitching a ride on the massive momentum of the host, operating in a tight, symbiotic envelope. The remora space architecture treats near-Earth asteroids like the sharks of the solar system.
It is a profound shift from the traditional orbit and observe model. These 6 CubeSats, each utilizing standard form factors, likely no larger than a shoebox or perhaps a small microwave oven.
Wait, they are that small?
Yeah, very small.
Yeah.
And they're not designed to fly across the solar system under their own power. They will hitch a ride on a larger launch vehicle into deep space.
Okay, so they get dropped off.
Once they are deployed in the vicinity of a targeted near-Earth asteroid, the swarm approaches the body. They don't just fly by. They rendezvous.
They match speed.
Yes. Depending on the specific mission profile, they might attempt to physically dock with the asteroid's surface using microanchors, or more likely, they will establish an incredibly tight, synchronized orbital formation just meters above the tumbling surface.
A swarm of space hitchhikers. I love that. But beyond just being cheap to build, there is a massive scientific advantage to breaking your sensors up into 6 tiny boxes instead of one big one.
There is a huge advantage.
Because if you have a single billion-dollar probe orbiting a rock, you are fundamentally limited to a single point of observation at any given millisecond. You have one pair of eyes.
Right.
You are taking a local measurement of the magnetic field or the gravity at one specific coordinate in space.
And that single point measurement creates ambiguity when you are trying to map a complex irregular body. But when you deploy a distributed swarm of 6 CubeSats, you instantly create a multi-static, multi-dimensional sensor network.
You're seeing it from all sides at once.
You are no longer observing the asteroid. You are enveloping it.
So how does enveloping it actually tell us what is inside the rock? How do 6 shoeboxes give us that internal structural map that the billion-dollar telescopes couldn't?
Through the extreme precision of gravitational multipole expansion.
Okay, you're going to have to translate that for me.
Let's break that down. Because the asteroid is an irregular rubble pile, its gravity is not uniform.
It's lumpy.
It's lumpy. If there is a massive, dense chunk of iron buried 50 meters beneath the surface on the northern hemisphere, the gravitational pull will be microscopically stronger in that specific localized area compared to the dusty, porous southern hemisphere.
Okay, so the gravity pulls harder near the iron.
Yes. As the 6 CubeSats fly in formation around the asteroid, their orbital paths will be slightly perturbed by these gravitational anomalies.
The dense iron chunk pulls one of the CubeSats slightly out of line.
Exactly. And the CubeSats are constantly communicating with each other, measuring the distance between themselves down to the millimeter using optical intersatellite links or precise radio ranging.
So they know exactly where they all are relative to each other.
By mathematically analyzing exactly how the swarm's formation deforms over time as they fly through the gravity field, you can solve for the specific mass distribution inside the asteroid.
Oh, wow.
You are essentially using the microscopic wobbles of the CubeSats to perform a localized gravimetric MRI of the rock.
An MRI? That's incredible.
You map the internal density, the voids, and the monolithic boulders without ever having to drill a single core sample.
That is mathematically beautiful. You use the chaotic nature of the asteroid's gravity as the scanning mechanism itself. But here is the massive operational hurdle that I immediately run into. Let's look at the logistics. We are talking about 6 independent spacecraft.
It's tiny ones.
They're flying in tight formation. They are mere meters away from a tumbling, irregularly shaped asteroid that has a chaotic, lumpy gravity field.
Right.
And they are doing all of this millions of miles away from Earth. If I think about a standard mission control center for a single lunar lander, I picture dozens of flight dynamics officers sweating over consoles, calculating orbital insertion burns, sending telemetry commands.
The whole NASA control room scene.
Exactly. Managing 6 distinct spacecraft in a highly perturbed deep space environment simultaneously, wouldn't you need an absolute army of human operators constantly adjusting their flight paths just to make sure they don't crash into a boulder or slam into each other?
The human operational cost is usually the silent killer of deep space budgets.
Right.
If you attempted to fly the REMORA swarm using traditional human-in-the-loop mission control protocols, that €50 million budget would evaporate in a matter of months.
Just paying salaries.
You would be paying the salaries of dedicated navigation teams working round-the-clock shifts. But the financial cost isn't even the primary barrier.
It's not.
The laws of physics outright prohibit manual control in this scenario.
Because of the speed of light.
Precisely. Deep space telemetry is constrained by the speed of light. If the asteroid is 15 million miles away, a radio signal traveling at light speed takes over a minute to get there, and the confirmation signal takes over a minute to get back.
So there's a lag.
You are operating with hard, unchangeable round-trip latency of several minutes. You cannot fly a spacecraft with a joystick when the lag is measured in minutes.
It's like playing a video game with terrible ping.
Worse. Imagine one of the CubeSats detects that the asteroid's irregular shape has caused a sudden, unexpected gravitational shear, and it is drifting toward a collision.
Okay.
By the time the onboard sensors register the danger, package the telemetry, beam it back to the Deep Space Network antennas on Earth, the human operator sees the red light flashing on their monitor, calculates an evasion burn, and transmits the command back to the CubeSat.
It's already crashed.
The spacecraft has already been obliterated against the surface.
The human reaction time, combined with the speed of light, makes remote control a death sentence. So to keep the budget at $50 million and to actually survive the environment, you have to completely sever the cord to mission control.
You have to push the intelligence to the edge. The swarm has to be fully autonomous.
Here's where it gets really interesting, because the solution to this isn't just basic autopilot. Autopilot on a commercial jet just holds a heading in a predictable atmosphere.
Right, it's relatively simple.
What the UK researchers are developing is an artificial intelligence survival mechanism. It is a software architecture known as NEAR, N-E-A-R, standing for Near Earth Asteroid Regions Software.
NEAR.
And the most critical function of the NEAR software is calculating fuel minimal reserves on the fly in a highly chaotic environment. This is life or death for a CubeSat.
Because they have almost no fuel.
Exactly. A massive flagship probe has large hydrazine tanks. If it makes an inefficient orbital correction, it just burns a little extra fuel. No problem.
Plenty to spare.
A CubeSat might only be equipped with a heavily miniaturized cold gas thruster system or an electrospray thruster. The total delta V, the total amount of thrust it can generate over its entire lifespan, is infinitesimally small. Every single microburst of propellant must be mathematically optimized.
The NEAR architecture allows the spacecraft to dynamically assess its localized environment, determine its required trajectory to maintain the sensor network formation, and execute the mathematically absolute minimum energy path to get there.
All on its own.
Entirely independent of Earth. This requires an incredibly sophisticated onboard processing capability, which the researchers have divided into 2 distinct coupled algorithmic engines. It's called DNIR and GONIR.
Okay, DNIR and GONIR, the dynamic modeling engine and the pathfinding engine. Let's dig into DNIR first, because modeling gravity around an asteroid sounds like a nightmare.
It is extremely difficult.
When we launch a satellite into Earth orbit, the math is relatively stable. Earth is a massive, slightly oblate spheroid. The gravity field is dominant and well mapped. Keplerian orbital mechanics work beautifully.
It's a solved problem.
Right. But an asteroid is a totally different beast. Some look like tumbling dog bones. Some look like rubber ducks. Some are just jagged, spinning shards of rock.
You are describing a non-Keplerian dynamic environment. Around a tumbling, irregular body, the gravitational potential field is wildly asymmetric.
Because the mass is all over the place?
And it's constantly changing relative to a fixed point in space as the object rotates. To survive, the CubeSat must constantly calculate the gravitational pull not from a single point mass, but from a complex polyhedral-shaped model.
It has to calculate gravity from every lump and bump.
DYNIR is the algorithmic engine that handles this. It takes the real-time optical and ranging data from the sensors, builds a continuous 3D mathematical model of the asteroid's shape, and computes the highly chaotic gravitational potential field that the spacecraft is currently swimming through. It maps the invisible, shifting currents of gravity.
It is the real-time cartographer of the void. It builds the topographical map of gravity. And once DYNIR builds that map, it feeds the data directly into GONIR.
Right. GONIR is the executive decision maker. It is the pathfinding brain.
So it looks at the map.
It utilizes advanced control theories, likely forms of model predictive control or convex optimization, to look at the map provided by DYNIR, look at its own critically low propellant gauge, and look at the desired orbital coordinate it needs to reach to maintain the swarm formation.
And then it plots a course.
It plots a trajectory that exploits the chaotic environment. Rather than just pointing at the destination and firing a thruster against the gravitational currents, GONIR calculates how to surf the gravitational waves.
Surf them.
It might wait for the tumbling asteroid to rotate just enough so that a local gravity anomaly actually pulls the CubeSat in the right direction, requiring only a tiny microsecond burst of the thruster to complete the maneuver.
It's like a master kayaker navigating Class V rapids.
That's a great analogy.
A novice kayaker just paddles furiously in a straight line, fighting the current, and exhausts themselves immediately. But the master kayaker reads the water.
They let the water do the work.
They see the eddies, the sheer lines, the rocks. They angle the nose of the boat just right, and they let the immense chaotic energy of the river itself do the work, slaloming through the danger with almost zero physical effort. GONIR is reading the gravitational rapids.
That is an exceptional analogy for the underlying mathematics of the optimization algorithms. And if we connect this to the bigger picture, the successful development of the DYNIR and GONIR software suite is arguably far more valuable than the physical €50 million hardware of the REMORA swarm itself.
Really? The software is worth more than the ships.
Because if you can definitively prove that this software can navigate non-Keplerian gravity and manage highly constrained resources without human intervention, you have just laid the foundational operating system for the entire future space economy.
You were talking about the infrastructure for asteroid mining.
Absolutely. If commercial entities are ever going to profitably extract water ice or platinum group metals from near-Earth objects, they will not be doing it with human astronauts, and they will not be doing it with remote-controlled rovers suffering from a 10-minute telemetry lag.
Too expensive and too slow.
They will use massive, autonomous industrial swarms, and those swarms will require the exact autonomous pathfinding and resource management logic being pioneered by the NIR architecture. This software is the key to unlocking scalable, deep space industrial operations.
But developing software that brilliant presents a massive engineering paradox on its own. You can write thousands of lines of incredibly elegant code. You can run millions of Monte Carlo simulations on supercomputers.
Sure, in theory.
But you cannot just load that code onto a €50 million physical swarm, strap it to the top of a rocket, blast it into the vacuum of space, and cross your fingers that you didn't miss a decimal point in the convex optimization loop.
Definitely not.
The vacuum is entirely unforgiving. A single line of bad code in GONIR, a thruster misfires for half a second too long, and your CubeSat shatters against a boulder. You have to physically test the hardware and the software working together.
It has to be validated.
But how do you test software designed to navigate the frictionless, tumbling microgravity environment of an asteroid when your laboratory is bolted to the surface of the Earth under the crushing, omnipresent pull of 1G?
You have to build a terrestrial environment that explicitly tricks the physical hardware into believing it is floating in deep space.
Trick the hardware.
And this brings us to another distinct advantage the UK possesses. At the University of Liverpool, where the lead authors of the REMORA proposal are based, they have constructed a highly specialized facility known as the Zero-G Astrolab.
The Zero-G Astrolab. I am fascinated by facilities like this because they sound like pure science fiction, but they are triumphs of material science and metrology.
They really are.
The absolute core of this laboratory, its defining feature, is what they claim to be the flattest floor in the UK.
The flattest?
And the best way to conceptualize how a floor helps test spacecraft is to imagine the ultimate obsessive-compulsive air hockey table.
An air hockey table. Well,
On a standard arcade air hockey table, a motor blows air up through hundreds of tiny holes, creating a cushion that a plastic puck floats on, eliminating most of the friction. The zero-G Astrolab inverses this concept with terrifying precision.
it inverses it.
The floor itself is an epoxy resin poured and cured to a self-leveling precision that approaches optical flatness. It is obsessively smooth.
So it's like a mirror.
Basically. Instead of the floor blowing air, you take a physical, heavy prototype of the CubeSat and you mount it on a specialized rig equipped with air bearings. This rig acts like a reverse hovercraft.
Oh, I see.
It forces a microscopically thin film of compressed gas down onto the epoxy floor.
This setup effectively nullifies kinetic friction. The prototype, weighing dozens of kilograms, is physically floating a fraction of a millimeter above the resin surface.
It's actually floating.
If you walk up to it and push it with the absolute lightest touch of your pinky finger, it will glide silently across the room at a constant velocity until it impacts the far wall.
Wow.
Exactly as it would if you applied that same force in the vacuum of space. The mass remains, but the friction is gone.
So the engineers take the actual physical subsystems, the optical navigation cameras, the gyroscopes, the miniature cold gas thruster valves. They mount them on this floating rig, and they load the near software onto the onboard processor.
Everything working together.
This is the holy grail of aerospace validation hardware-in-the-loop testing.
The necessity of hardware-in-the-loop testing cannot be overstated when dealing with autonomous systems. It is one thing for Dyneer to plot a perfect trajectory in a purely mathematical simulation.
Because computers are perfect.
In a computer, sensors do not have thermal noise. Thruster valves open and close instantaneously with zero mechanical latency. The minimum impulse bit is always perfectly calculated. But physical reality is chaotic and messy.
Things break.
Hardware degrades. A star tracker camera might catch a stray reflection. A solenoid valve might stick for 3 milliseconds.
And that's all it takes to crash.
Hardware-in-the-loop testing forces the pristine software algorithms to interact with the messy, noisy realities of the physical world. As the prototype glides across the epoxy floor, the optical sensors must process actual photons from the room.
But Dyneer software has to actually think.
Yes. It must calculate a trajectory, and it must command actual physical gas to expand through a nozzle to alter the prototype's momentum. It proved that the digital brain can successfully command the analog body.
I see the value in that, absolutely. But I have to play devil's advocate here because there's a glaring limitation to an air hockey table, no matter how flat the epoxy is.
Of course.
Space is a six-dimensional environment. A spacecraft moves with 6 degrees of freedom. It translates forward, backward, left, right, up and down, and it rotates by pitching, yawing, and rolling.
The 6DOF environment.
Right. When you bolt a prototype to a flat floor, you are trapping it in 2 dimensions. It can slide along the X and Y axis, and it can spin like a top around the Z axis. That is only 3 degrees of freedom.
It can't go up.
It cannot pitch forward. It cannot fly upward. How can engineers possibly trust software to navigate the complex 3D tumbling of an asteroid when its physical body has only ever been tested on a flat plane?
That is the fundamental critique of air-bearing testing, and it is a challenge aerospace engineers have wrestled with since the Apollo program. A planar floor cannot perfectly replicate volumetric space.
So how do they fix it?
However, we bridge the gap between 3 degrees of freedom and 6 degrees of freedom using highly advanced coupled mathematical models, specifically utilizing Euler's equations of rigid body dynamics.
Euler's equations, okay.
Here's how the methodology works. You are isolating the variables. You use the flat floor to absolutely rigorously validate the planar dynamics. You prove beyond a shadow of a doubt that the sensor fusion, the processing latency, and the thruster impulse bits work flawlessly in the X, Y, and yaw dimensions.
Okay, so you know the flat parts work perfectly.
Once you have mathematically validated the physical hardware's performance in that constrained 2D plane, you extract that precise performance data. You then feed that validated real-world hardware data back into a massive 6-degree of freedom supercomputer simulation.
So you prove the machine works horizontally in the real world, and you let the math prove it works vertically in the simulation.
Exactly. Because the physics of a thruster firing or a sensor reading don't fundamentally change just because the object pitches forward.
That makes sense.
If you can eliminate the uncertainties of the hardware latency and the software execution loops on the floor, the mathematical extrapolation to 6DOF becomes highly reliable. It is the absolute best terrestrial proving ground available, short of actually launching the prototype into orbit.
Which returning to our initial constraint, would blow the 50 million euro budget immediately.
Immediately, yes.
The constraints dictate the innovation. Okay, so let's synthesize where the architecture stands. The UK possesses the theoretical models. They have the Dyneer and Gonneer software actively learning to surf chaotic gravity.
Right.
They have the Zero-G Astrolab in Liverpool physically validating the hardware in the loop on the smoothest epoxy available. They have the REMORA swarm concept finalized, but it's still just a brilliant concept trapped in a laboratory.
Still on the ground.
How do you actually get a 50 million euro fleet of tiny metal boxes out of Earth's gravity well? You cannot afford to buy a dedicated heavy lift rocket. You need a ride.
And this requirement activates another vital node in the UK's domestic space ecosystem, the Small Satellite Industrial Cluster, located in Surrey.
Sir.
For decades, the region surrounding the University of Surrey, spearheaded by companies like Surrey Satellite Technology Ltd. Or SSTL, has been a global pioneer in miniaturized low-cost space hardware.
They wrote the book on doing space cheaply and reliably.
They did. Long before CubeSats were a standard university project, Surrey was proving that you could use commercial off-the-shelf components to build robust satellites. And the REMORA white papers brilliantly leverage this existing domestic infrastructure.
How so?
They propose what is known as a phase row pilot study. Because the REMORA CubeSats are built to standard form factors, they do not require custom launch integration. They utilize standard deployer boxes.
So they can just plug into any rocket.
The strategy is to integrate these autonomous REMORAs as secondary payloads hitchhikers on future, larger SSTL missions. When a primary commercial or government satellite is launched, there is almost always excess mass and volume capacity inside the rocket's payload fairing.
Empty space in the trunk.
Often, standardized mounting rings, like the ESPA ring, are used to bolt secondary payloads around the primary one.
It is the orbital equivalent of carpooling. You don't buy the bus, you just buy a ticket for the empty seat in the back. And structurally, this mitigates an enormous amount of financial risk. If the launch vehicle suffers an anomaly and explodes on the pad, or if the REMORA swarm fails to boot up once deployed in the vacuum, you haven't lost a flagship sovereign mission.
You've lost a 50 million secondary experiment.
Right. The primary mission of the rocket still succeeds. It allows the UK to incrementally validate this radical autonomous technology without betting the entire science directorate's budget on a single launch.
It is an incredibly pragmatic, low-risk pathway to orbit. But while the engineering validation must be careful, methodical, and incremental, the geopolitical and planetary realities driving this mission are anything but patient.
No, we are running out of time.
There is a very real, very pressing urgency to get the near architecture and the swarm telemetry functional. And this shifts our analysis from the theoretical mechanics of CubeSats to the immediate ticking clock of planetary dynamics.
A ticking clock. We alluded to this in the introduction, but we need to stare directly at what is hurtling toward us in the year 2029.
Yes, we do.
This is not some arbitrary date selected by bureaucrats for a funding cycle. The United Nations has officially designated 2029 as the International Year of Asteroid Awareness and Planetary Defense.
A very specific title.
And they did not make that declaration lightly. They get it because in 2029, humanity is going to receive a visceral, undeniable wake-up call regarding our fragility in the cosmos.
We are preparing for the close approach of the asteroid Apophis.
Apophis. The name alone carries a certain mythological weight. Apophis was the ancient Egyptian deity of chaos and darkness. And for a brief period after its discovery in 2004, the asteroid absolutely lived up to that name. Early orbital calculations indicated a terrifyingly high probability, reaching up to almost 3% at one point, that Apophis would actually impact Earth in 2029.
Which is terrifying.
Okay.
But subsequent, highly precise radar observations eventually ruled out a direct impact for the 2029 encounter.
Thank goodness.
And later observations ruled out impacts for the subsequent passes later in the century. However, the relief of avoiding an impact does not diminish the sheer staggering reality of the orbital geometry we are about to witness.
It's still coming close.
Very close. Apophis is not a small chunk of gravel. It is an S-type asteroid with an estimated diameter of roughly 350 meters. That is over 11,150 feet across.
I try to visualize that mass. You have to picture the Eiffel Tower or the Empire State Building ripped from its foundations, composed of tens of millions of tons of silicate rock and nickel iron, tumbling through the vacuum at tens of thousands of miles an hour.
It's a flying mountain.
And the trajectory of this mountain during the 2029 pass is what makes it a generational event.
To contextualize how close it will come, we have to look at humanity's own orbital infrastructure. When you look at satellite television or check global weather patterns, you are relying on satellites placed in geostationary orbit. This is a specific orbital regime located roughly 36,000 kilometers, or about 22,000 miles, above the Earth's equator. At the precise altitude, the satellite's orbital velocity matches the rotational speed of the Earth, allowing it to stay parked permanently over one specific geographic location.
The geostationary belt.
We have an entire ring of multi-billion-dollar hardware occupying that belt. During the 2029 encounter, the trajectory of Apophis will bring it inside that geostationary belt.
Wait, inside, it is going to thread the needle.
Yes.
It will pass less than 20,000 miles from the surface of our planet. That is closer to us than the satellites beaming the weather report. A 1,000-foot mountain is going to skim just over the top of our atmosphere, plunging through the very space we consider our domestic orbital territory.
The gravitational interaction alone will be intense. Earth's immense gravity will physically grab Apophis, radically altering the asteroid's orbit, and likely triggering localized seismic events, asteroid quakes across its surface, potentially rearranging its surface boulders and structure in real time as it flies past.
And the most profound aspect of this encounter won't be recorded on a seismograph. It will be recorded by human eyes.
Exactly.
Because Apophis is so massive and passing so close, it will cross the threshold of naked eye visibility across massive swaths of the globe, including parts of Europe, the UK, and Africa. Millions of people will be able to walk out of their homes, stand in their backyards, look up at the night sky, and clearly see a point of light moving rapidly across the backdrop of stars.
No telescopes need.
No telescopes, no binoculars, just standing on the grass watching a civilization-ending amount of kinetic energy silently glide past the atmosphere.
The psychological and cultural impact of that visual will be unparalleled. Intellectually, the global public understands that asteroids exist. We've all seen the CGI representations in movies.
Sure, Armageddon, Deep Impact.
But there's a massive cognitive dissonance between knowing a threat exists theoretically and physically standing in your garden watching a 350-meter rock fly between Earth and our own communications satellites. It will crystallize the absolute necessity of planetary defense architecture in the public consciousness overnight.
We won't be able to ignore it anymore.
It will be the ultimate validation that space is not empty and that we are incredibly vulnerable.
It is going to be a shared global moment of held breath. But as terrifying as watching Apophis will be, the asteroid experts and planetary defense researchers I talked to are not the ones losing sleep over 2029.
No, they aren't.
Because Apophis is a known variable. We have mapped its trajectory. We know the mass. We know the hour and minute of its closest approach. The true existential dread, the nightmare scenario of planetary defense, does not originate from the mountains we can see. The nightmare comes from the rocks we are entirely blind to.
Which forces us to confront the most dangerous vulnerability in our entire global observation network. We have spent decades building an incredibly robust, highly sensitive system of ground-based optical telescopes and sky surveys.
We have eyes everywhere.
They relentlessly scan the night sky, peering deep into the outer solar system, cataloging millions of near-Earth objects. But there is a fundamental geometric limitation to this system. All of those ground-based optical telescopes operate on the night side of the Earth, looking outward, away from the inner solar system.
Because if you take a highly sensitive, multi-million-dollar optical sensor designed to detect the faint reflection of a rock millions of miles away, and you point it toward the inner solar system during the day, you are pointing it directly at the sun.
It would be disastrous.
It would be like staring through a high-powered sniper scope directly into a stadium spotlight while trying to spot a dust mite fluttering an inch from the bulb. The sensor would be overwhelmed instantly. The optical glare is blinding.
This creates what astronomers refer to as the sunward blind spot. It is a massive volumetric cone of space extending from Earth toward the sun, encompassing the solar elongation angles, where the sun's radiation and scattered light in our atmosphere completely obliterate any possibility of optical detection.
So anything coming from that direction is just invisible.
Any celestial body occupying an orbit that brings it toward Earth from within that sunward cone is effectively cloaked. We cannot see it. And this is not a theoretical vulnerability debated in academic papers. This blind spot has already been violently exploited,
It already happened.
resulting in a direct impact on a populated city with absolutely zero warning.
We have to talk about Chelyabinsk. February 15th, 2013. A typical freezing winter morning in the industrial city of Chelyabinsk, Russia. The sun is just rising over the horizon, casting long shadows.
A normal morning commute.
People are scraping ice off their windshields, driving to work, and then the sky absolutely detonates. A streak of light, momentarily burning brighter than the sun itself, tears across the upper atmosphere. For a few terrifying seconds, the intense light casts moving shadows in the wrong direction across the city.
And then silence.
Because light travels infinitely faster than sound, there is an agonizing 3-minute delay where the trail of superheated plasma fades into a thick, twisting column of smoke. And then the acoustic shockwave hits the ground.
To understand the violence of that shockwave, we have to look at the physics of the object. This was an ordinary chondrite meteor, roughly 20 meters or about 65 feet in diameter.
Is it relatively small?
Yes. It entered the Earth's atmosphere at a shallow angle, traveling at an estimated 40,000 miles per hour. As it plowed into the thickening layers of the atmosphere, the air in front of the rock could not move out of the way fast enough.
It just slammed into the air.
It compressed violently, creating immense ram pressure and superheating the air into a plasma envelope. The aerodynamic stress acting on the front of the meteor rapidly exceeded the internal tensile strength of the rock itself. At an altitude of roughly 18 miles above the surface, the structural integrity failed completely.
The rock broke.
The meteor did not just crack apart, it violently pancaked and detonated in what we call an airburst. The sudden release of kinetic energy was staggering, estimated at nearly 500 kilotons of TNT equivalent.
That is more than 30 times the destructive energy released by the atomic bomb detonated over Hiroshima.
30 times.
And that energy propagated downward as a physical wall of overpressure. When the shockwave reached Chelyabinsk, it blew in the windows of thousands of apartment buildings, schools, and commercial structures across hundreds of square miles.
The destruction was massive.
The roof of a massive zinc factory collapsed entirely. Over 1,400 people required medical attention, the vast majority of them suffering lacerations because they had seen the initial blinding flash of light, walked to their windows to look outside, and were standing directly behind the glass when the pressure wave arrived and shattered it inward.
Just a horrific sequence of events.
It was an incredibly destructive, highly documented kinetic event caught on hundreds of Russian dashboard cameras. But the most terrifying aspect of the Chelyabinsk event isn't the damage itself. It is the intelligence failure leading up to it. With all of our sky surveys, with all of our orbital mechanics models, no one, not NASA, not the ESA, not the Russian military radar network saw it coming. It was a complete surprise.
This raises an important question. How does a 65-foot rock, traveling at 40,000 miles per hour, slip entirely undetected through the most technologically advanced sensor network in human history and detonate with the force of a thermonuclear weapon over a city of over 1 million people?
Because of its trajectory.
Yeah.
It came from the sun.
Precisely. Its specific orbital path, its radiant approach to Earth from the daylight side, it spent its final approach entirely hidden within the sunward blind spot.
Hiding in the glare.
The telescopes on the night side of the Earth were looking the wrong way, and no optical telescope on the day side could penetrate the solar glare to track it. We were completely structurally blind to that vector of attack.
So what does this all mean? We have established the catastrophic danger of the sunward blind spot. We have the looming psychological wake-up call of Apophis in 2029. And we have this incredibly elegant €50 million proposal out of the UK for a swarm of autonomous, artificially intelligent CubeSats designed to operate independently in deep space.
Right, the pieces are all there.
When you overlay those three realities, the ultimate strategic purpose of the REMORA architecture suddenly snaps into crystal clear focus. REMORA is not just a scientific mission to map the gravity of a random asteroid. It is the blueprint for a planetary sentinel system.
The genius of the €50 million swarm architecture is its scalability and its autonomy. Because these CubeSats are incredibly cheap to manufacture, and because the near software eliminates the need for massive human mission control teams, you are not limited to sending them on bespoke scientific excursions to known targets like Apophis.
You can just pump them out.
You can mass-produce these swarms and deploy them strategically to plug the gaps in our planetary defense network.
You could launch a fleet of REMORA CubeSats and maneuver them into a trailing orbit behind Venus, or park them at the L1 Lagrange point between the Earth and the Sun.
Put them right in the danger zone.
You position them entirely outside the optical glare of the Sun from Earth's perspective.
And you turn them around. You have them look outward, away from the Sun, scanning the exact volume of space that Earth-based telescopes cannot see. They become a synthetic aperture optical barrier.
A tripwire.
If a Chelyabinsk-sized rock, or something much larger, is hurtling toward Earth from the dayside, the Weber fleet detects the thermal signature, or the optical reflection, against the blackness of space. The Gone-Ear software independently calculates the trajectory, recognizes the threat vector, and beams an encrypted early warning telemetry packet back to Earth.
Days or even weeks before the object enters the atmosphere.
They serve as the eyes we currently lack.
They are the early warning radar for the sunward blind spot. But to bring this entire massive concept back down to Earth, we have to inject a heavy dose of fiscal reality into the conversation.
Yeah, the budget part.
A mathematically brilliant architecture capable of revolutionizing planetary defense and autonomous resource mapping is ultimately still just ink on a white paper until someone writes the check to bend the metal. And given the intense budgetary constraints and shifting political priorities currently facing the UK space sector, finding even the seemingly minuscule amount of 50 million euros to fund a new, dedicated sovereign mission architecture from scratch is an uphill battle.
It is incredibly difficult right now.
It requires immense political will to prioritize planetary defense over more immediate terrestrial concerns. It is highly uncertain if the UK Space Agency will be able to natively fund the REMORA mission through its entire life cycle in the near term. Navigating the labyrinth of government funding pipelines often proves far more treacherous and chaotic than navigating the non-Keplerian gravity field of a tumbling asteroid.
That is the harsh reality of aerospace procurement. However, the intellectual heavy lifting has already been accomplished.
The math is done.
The teams at institutions like the University of Liverpool are not developing the NEAR software suite or validating the hardware-in-the-loop protocols in a vacuum. Even if domestic funding falls short, the REMORA architecture, the algorithms bridging 3DOF testing to 6DO simulation, the autonomous fuel optimization loops, the multi-static gravity mapping techniques is fully designed.
The blueprint exists.
And if the UK cannot launch it independently, there is a strong probability that other entities will recognize the immense value of this work. International space agencies looking for low-cost auxiliary fleets to accompany their flagship missions, or private aerospace consortiums aiming to deploy the first autonomous asteroid mining swarms, could adopt and integrate this brilliantly optimized architecture. The foundational technology is primed and waiting for the right backer to recognize its potential.
We have covered a truly immense amount of conceptual territory today. We started by looking through the tinted skyscraper glass of our current remote sensing limitations, understanding why we cannot just look at the outside of a rock to know how to deflect it.
You get to get inside.
We explored the elegant UK solution to the funding paradox, mimicking the symbiotic REMORA fish to deploy a 50 million euro multi-static sensor network of CubeSats. We dived into the deep mathematics of the NEAR software, watching artificial intelligence learn to surf chaotic gravity, and we slid across the microscopic perfection of the zero-G Astrolab's epoxy floor. We confronted the ticking clock of Apophis, threading the needle of our geostationary belt in 2029, and the violent, terrifying reality of the sunward blind spot that Chelyabinsk exposed. It is a journey from the absolute limits of human vision to the bleeding edge of autonomous survival in the void.
It serves as a remarkable testament to the ingenuity forced by constraint. But the implications of this technology force a profound shift in how we must conceptualize our future interactions with deep space. I want to leave you with a thought that extends far beyond the engineering schematics and the budget proposals.
Okay, lay it on us.
If autonomous architectures like the REMORA swarm become the standard operational model for deep space, if we successfully populate the solar system with tiny self-contained silicon brains that make their own independent fuel-minimal survival choices, mapping chaotic gravity wells, and calculating complex orbital trajectories millions of miles away from any human oversight, surviving entirely on their own in the dark for years at a time.
Yeah.
At what specific point do we stop classifying them merely as human tools? At what point does the complexity of their autonomous behavior force us to view them as a new, independent artificial ecosystem living symbiotically alongside the ancient rocks of our solar system?
Are they just programmed machines, or are they the vanguard of the first artificial species we are seeding into the wild, chaotic ocean of space? It is a fascinating and slightly haunting philosophical threshold, and it brings us right back to the image we started with. The next time you step outside on a clear night and look up into the dark, remember that you are not looking at an empty, static void. You are looking into a deep, silent ocean filled with massive momentum where ancient mountains hurtle through the pitch black. But hopefully, in the very near future, the fragile glass boat of our planet won't be relying solely on a weak flashlight pointing in the wrong direction. Hopefully, we will have our own fleet of highly intelligent mechanical fish swimming out in the dark, watching the currents, and ensuring that nothing ever slips out of the sun to take us by surprise again. Thank you so much for joining us on this exploration of the universe. Keep looking up, stay curious, and we will catch you next time.